All right, next example. Okay, find the absolute extreme values of the following functions. Now, this example is going to be the most difficult of these three, at least if it's like the last lecture. On the interval -5 to 5. Or if you have any questions about the previous example, you can also ask that. Let's start with this example again. Again, I'm going to give you some time to work on it yourself, right? This is how the online lectures are from now on. Getting dirty with the math. Timer. I will give you a little bit longer. Let's do an extra 30 seconds. So when you find the critical numbers, um, make sure you're very careful with that. That's all I'll say as a general hint. If you do have questions, you can ask. I'll make the poll active at some point during the timer. Just gonna put the poll options on the screen now. But again, if you're still working on it, I encourage you to finish your work and then answer the poll. Okay, so that's it for the timer. So if you haven't answered the poll, I'll just answer that. So as the results trickle in, the last results, I'll kind of write the percentages on the screen. So I can definitely tell that that problem was a lot more difficult for all of you. Given, so first of all, a lot of people were waiting until the very end to answer the poll, and then just given the actual questions, or sorry, choices they actually put. So at the moment, we have 48 out of 63 responding, so give or take, three quarters. So we have 0% actually doing choice A, which is good, right? Everyone should know how to start, right? You know how to find the derivative first, and then use that to find the critical numbers. We have 20. Sorry, whoops. We have 44% saying they get stuck on finding the critical numbers. We have 6%, 6%, and 21%. Okay, so the bulk of everyone in the chat seems to be at choice B. I can start, but can't get the critical numbers. Okay, so the reason why this problem is so much more difficult is because of that step, finding the critical numbers. So before we go into the full details, so a new screen should be appearing in a second. Okay, so I want to actually show you where to find this in Canvas, other than just tell you, oh, go look it up. So this is our Canvas site. Obviously, I see a lot more on the left side than you because all this stuff is hidden from you. In fact, let's go to student. Okay, so this is what you see as a student. So if I go to modules, so this is just like what you did to watch the videos, right? We go to section 4.1. All right, and then once you open the screen, obviously these are the videos you watched, and then you have this supplemental material. So the first link, the lecture notes, those are essentially the lecture notes we're going over today. In the written lecture notes, there are some other extra examples, so I do encourage you to look at those lecture notes for more examples and more practice. But then there's this other thing, so optional mean value theorem. So if something says optional, it truly is optional. It's not part of the course. Mean value theorem is no longer part of the course, but I put it there just in case you're interested. If something says extra notes, though, that's not optional. Extra notes means those are notes. Just they're usually good as a kind of like a 1 or 2 page, just kind of not in the main part of the notes because it would be just too much of a break. The big thing about these notes, which I'll now bring up on the iPad screen. Okay. So the notes that I just showed you how to find on Canvas. So the extra notes for this section, that's down here. So these notes talk about non-differentiable functions. So I said in the very first example, for most questions or most functions that you will deal with in this class, when you do the critical numbers or find the critical numbers, when you answered the question, where does the derivative not exist? The answer to that question is most often going to be it exists everywhere, right? We had a polynomial in the first example, a rational function in the second example, but you should be aware of the examples. Well, when is the answer not none? When do I actually have an answer for that question, right? In particular, what types of functions are actually continuous but not differentiable? And there are 3 types of functions you need to be on the lookout for, and these notes kind of go through them. So we've talked about graphically. In the past, we've said, okay, graphically, you should be on the lookout for, let me circle this, be on the lookout for corners and cusps, right, graphically. But if you don't have a graph of the function, how would you know a function has a corner or a cusp? So one such way that that can happen is if you have an absolute value. If there's an absolute value somewhere in your function, that means there's going to be some sort of corner or cusp in your function. And how do you find the locations of that corner or cusp? Well, this actually explains how. This g of x equals 0. Now, what is g of x? That is the inside of the absolute value, if you look at this example here. So looking at, say, this right graph. Let's look at a specific example. Notice that this is the graph of the function y equals absolute value of x squared minus 4. If I were to set the inside of the absolute value to 0, I would get -2 or 2, right? I get x squared equals 4. So notice that at x equals -2 and 2, I have cusps. So anywhere where an absolute value is equal to 0, right? That means you can get a cusp or a corner. Now, the function that we're dealing with in our example in the other notes does not have an absolute value. It actually falls into the second category. A power function, in other words, a function that has x to some power, where that exponent is between 0 and 1. And the reason, again, is because such functions, if I look at all three of these graphs, if I have an exponent that's between 0 and 1, again, those types of functions, you get corners, cusps, vertical tangents. The same idea occurs. So let's actually now go back to the actual example, and we'll talk about that specifically. Okay, so this was the example we were looking at. So notice that this actually does have an exponent that is less than 1, 2/3. So that means we're going to get a critical number if I set the inside of that exponent to 0, not the whole thing, just the inside of the absolute value. Sorry, the exponent. If I set the inside of that exponent to 0, I get critical numbers. And that's only because the exponent is between 0 and 1. Now, that's a lot to take in. So let's actually write some of this down. And then there'll kind of be another way we can remember this that's maybe a bit shorter. What if you didn't remember all of that stuff about, if the exponent is less than 1 or absolute values? Well, what is the derivative of this function? I need it anyway to find the critical numbers. So the derivative of this function is 2/3 times x squared minus 16 to the -1/3 times 2x, right? And if I rewrite this, so the 2/3 and the 2, they combine to give me 4/3, and then I get x over x squared minus 16 to the 1/3. So I'm writing the negative exponent really in the denominator. So this is my derivative. Now, when you answer the question, what are the critical numbers? There are two types. Where does the derivative not exist? Where is the derivative equal to 0? Now, if you're actually looking at this derivative, now it should be much easier to figure out where does the derivative not exist? Well, I have a denominator here. Anywhere that denominator equals 0, I'm not going to have a derivative, right? F prime won't exist. So I put x squared minus 16, set the denominator equal to 0. That gives me x equals 4 and x equals -4. That's kind of a quicker way to figure out that the derivative does not exist at certain points. So naturally, if you have an exponent that is less than 1 in the original function, naturally that will give rise to a derivative with some sort of denominator, right, that you could set equal to 0 to answer this question. As for the other type of critical number,
so like since we have stuff that doesn't exist within the interval, does that mean we just like can't do it anymore, or can we actually do it?
That's a good question. So in the last minute of class, I'll actually answer that question instead of going through the rest of the problem. We can finish it up on Friday. So the question was, does this mean we can't actually do the problem? We can do the problem as long as the function is continuous. So keep in mind that if the exponent is bigger than 0, as long as the exponent is either 0 or positive, the function is continuous, right? This function just has a cusp at -4 and 4. The function is continuous. It just so happens that the derivative does not exist there. The extreme value theorem doesn't apply if you don't have continuity, but we do have continuity, right? The issue is we don't have differentiability. And that comes into play because now we have non-trivial critical numbers. So that does put us right at time at 12:50. So that was the hardest part of that problem, I think. So it's good we got that part. I will briefly finish the problem on Friday.